Okay, we're going to be looking at if a molecule is polar. Now, previously we looked to see if a bond was polar, and just recall, a bond was polar if you're talking about two nonmetals, first of all, and if there was a difference in electronegativity. And if you recall, we drew dipole moments to indicate, I'm going to do the whole Lewis structure here, but we drew a dipole moment and we put the arrowhead toward the more electronegative thing. We said a little bit negative, a little bit positive, and we said that that bond is polar because this had a value of 4 on the electronegativity table, and that had a value of 1.2. Now what we're going to do is we're going to say, okay, the bonds are polar, but put into a molecule with that particular shape, is the molecule polar? And it's really going to depend on the shape. So I don't have a lot of room here, so I'm going to just continue to erase and draw. But how can we tell if a molecule is polar? Well, what we do is we visualize it, or you can build it, and you look at every bond and you look at the dipole moment of every bond, and you could draw that in or kind of visualize it. But then what you do is you take the entire molecule, you put a line through the middle of it, and decide, is one side a little bit positive and one side a little bit negative? It won't be a full positive or negative because that's for ionics, but is one side a little partially positive, the whole entire side, and is the other side a little bit, a little bit negative? Okay, and if that's the case, if we can divide up the molecule and say that part of it's positive and part of it's negative, then it's polar. But if I can't divide it up with a line, I can't have positives on one side and negatives on the other. I've got a positive and a positive on both sides, or negatives on both sides, then it isn't polar. So let's take a look at a couple of examples and try to visualize what this looks like in 3D. And when you build them on Friday, kind of take a look at whether that molecule is polar. So trigonal pyramidals and V-shapes tend to be polar. So let's take a look at a V-shape, and we'll look at a trigonal pyramidal. This is a water molecule. This is its Lewis structure. I'm trying to draw it so that it looks three-dimensional. And if we were to draw the dipole moments in, I would draw an arrow up toward that, arrow up toward that. That's a little bit negative, and these are a little bit positive. So it doesn't take a lot of looking at this to realize that if I were to draw a line right through the middle of the molecule, on this side I'd have negatives, and on this side I'd have positives. This is a polar molecule. So if there's a way you can draw a line right through the middle of the molecule, and I can get negatives on one side and positives on the other, no matter which side or which, because these are three-dimensional, then it's polar. So that's why V-shapes tend to be polar. Now, looking at a trigonal pyramidal, and if you can visualize it right now as we're even talking, you can see that that's going to be generally a polar molecule too. Of course, as long as the bonds are polar. But, most of the things, if there's a difference in atoms, then it's going to be polar. The bond will be polar. Okay, so nitrogen has a value of, I don't really have to remember off the top of my head, I think it's 3. And hydrogen has a value of 2.1. So you know that the dipole moment is coming up like this. Now, it's really important to know or visualize what that structure is so that you can see, look, this is negative up here, and down here we've got a little bit partially positive for all the hydrogens. So as I draw a line through this, what I find is the top part here is negative, and the bottom part here are positive. So this is a polar molecule. Because of the shape, provided that the bonds are polar, but generally they are, the shape is going to tend to make the molecule polar, making sure the bonds are polar to start with. Now, two shapes that generally are not polar, and again I'm going to try to draw it so they look three-dimensional, is tetrahedrals and trigonal planars tend to be nonpolar. Now, I've said here if all the bonds are identical, and we'll kind of explore that on Friday, but if you look at, let's just do a tetrahedral here. I've got just our methane. Again, I'm trying to draw it so it looks a little bit three-dimensional. Now, carbon is actually, I think, a 2.5 and hydrogen's a 2.1. So there's not a huge difference in electronegativity, but there's some. So the dipole moment would actually go in toward carbon because carbon's a little bit more electronegative. And what you'd find is that you'd have little partially positives. I won't go through and draw all the little deltas, but a little bit partially positive at all ends there. So if you build this or can visualize the tetrahedral from yesterday, you got like a little tripod with a camera on top. There is no good way for me to break this up. Any way I try to break it up, I have positives on one side and I have positives on the other side. So even though the bonds are polar, the molecule is not polar. So I'll come over here and do a trigonal planar, and maybe that will you can also see that that's not going to be polar. Okay, I'm not going to draw the lone electrons in, they should be there. So with this one, sulfur, or oxygen actually is a little more electronegative than sulfur, if we look at the values. So what we find here is, again, I'm not going to do the deltas, this is only partially negative. But what we find is the electrons get kind of pulled outward like so, and we have a little bit negative here, here, and here. So if you look at this and try to divide it up, there's no good way to divide this up. It's just not going to work that you have positives on one side and negatives on the other. You're going to have negatives on both sides. So this is a nonpolar molecule. Linear kind of depends. You do have to look at the dipoles. So linears can be a little bit tricky to figure out. Carbon dioxide is not polar. And I'll draw this and hopefully you'll see. Okay, I won't do all the lone electrons. But if we draw the dipole moments, oxygen's a little bit more electronegative than carbon. So we see a little bit negative here, a little bit negative here, partially positive here. And as you see, being a linear molecule, there's, I'm dividing it up, but I have negatives and negatives. Okay, I'm not going to have positives on one side and negatives on the other. So CO2 is a nonpolar molecule. And we actually are going to be using this information next chapter too, so make sure that you're really trying to understand when you build these if it's polar or not, because that's going to have a lot of impact on the next chapter. HCN, carbon is more electronegative than hydrogen, and nitrogen's actually more electronegative than carbon. Look up the numbers. So what you basically get is a pull toward the nitrogen away from these guys, hydrogen and carbon. So there's a net pull over here. So as you go to break this one up, you see you do have negatives on this side and positives on this side. So HCN is polar. You'd have HF if you had like something like that. And of course, that is just one bond and it is polar, right? Fluorine's more electronegative. Okay, so a little chart. Are the bonds in the molecule polar? Is there a difference in electronegativity? And like I said, most of the time there is. The diatomics H2N2O2, those wouldn't have electronegativity difference. But most do. So are the bonds polar? Yep, if they are. Is one side of the molecule partially positive, the other side negative? Yep, it's polar. And no, it's not polar. So again, these are going to tend to be the trigonal pyramidals and the V-shapes. These are going to tend to be the tetrahedrals and the trigonal planars. And linears, it kind of depends. Draw it out and see. Does that apply? If the bonds aren't polar, the molecule can't be polar. So H2N2O2, there's a couple others, but there's no way. If the bonds aren't polar, the molecule has no way to be polar.